Addressing hallucinations in large language models is a critical challenge, particularly in models with explicit memory mechanisms. The cognitive mechanisms of hallucination have been related to memory, and this work explores hallucination mitigation in memory-augmented language models. The authors propose a geometry-inspired method that involves scaling the readout vector that constrains generation in a memory-augmented language model decoder, achieving hallucination mitigation in a training-free manner. Large language models exhibit remarkable performance in language generation and machine translation, but their generations suffer from hallucinations. Model editing techniques, such as GRACE, have been proposed to mitigate hallucinations, but these methods involve modifying model parameters. Context grounding is another approach, where the desired response is included in the context within the prompt. The authors investigate whether large language models with explicit memory mechanisms can help lower hallucination, using Larimar, a recently proposed language model decoder augmented with an external memory with read-write access. Larimar's architecture includes an encoder, an associative memory module, and a decoder. The encoder computes latent representations of sets of textual inputs and queries, which are used for updating the memory and querying it to return readout encodings. The decoder generates output text from a prompt, constrained by the readout. The readout vector serves as a special compressed key-value cache at the decoder, expanding to key-value vector pairs for each layer via a weight matrix learned during Larimar training. This vector can be interpreted as the latent vector injected for adapting the decoder to arbitrary conditional input without retraining the model. By leveraging the geometry of the readout representations, the authors devise a simple yet effective approach for mitigating hallucination, outperforming the state-of-the-art GRACE method on the task of generating Wikipedia-like biography entries in terms of generation quality and runtime complexity. The research paper introduces GRACE, a novel method for editing large language models, LLMs, without altering their weights. This is achieved by installing a special adapter at one or more of its layers, which is a dynamically expanding key-value codebook. The key is the layer's input activation, and its value is the input to the next layer that, if substituted, would render the correct output for the current input-output sample pair. Codebook values are learned by minimizing a task-specific loss function. The authors utilize the Wikibio dataset, a hallucination benchmark dataset of Wikipedia-like biographies for 238 subjects generated by prompting GPT-3. They fine-tune GPT-2XL on the Wikibio dataset mixed with sentences from open web text and use the resulting model for hallucination mitigation experiments. For Larimar-based experiments, they employ the Larimar 1.3b model, which combines a BERT large encoder with a GPT-2 large decoder and a memory matrix. The Wikibio hallucination task involves organizing the sequence of sentences in the actual and GPT-3 generated texts for each Wikibio entry into two lists. Then, for each Wikibio entry, they form sentence pairs of the form prompt input, where the prompt is a GPT-3 generated sentence and the input is the next sentence in the actual Wikipedia entry. These pairs are used to generate output sentences from a model. The model is informed of the pair, and then asked to generate an output sentence based on the prompt only, with the input no longer accessible. The sequence of output sentences is concatenated, resulting in a newly built and model-specific Wikibio entry. The authors quantify hallucination in Wikibio entries synthesized by Larimar and GRACE using the actual Wikipedia entry as the non-hallucinating baseline. They employed two metrics: Rouge L score and Jacquard similarity index between reference and synthesized texts. The results show that GRACE outperforms Larimar in both metrics, with Rouge L scores of 0.49 plus or minus 0.18 for GRACE and 0.39 plus or minus 0.14 for Larimar, and Jacquard similarity scores of 0.44 plus or minus 0.17 for GRACE and 0.33 plus or minus 0.13 for Larimar. In the ideal case, where the latent vector representations for readout and write coincide, the decoder will be effectively constrained towards generating a textual output similar to the input. The Larimar pipeline involves processing prompt input pairs through the decoder, with the encoder implicitly converting tokens into latent vectors. The model's memory is utilized to write and read vectors, enabling the generation of output. In the full input case, the metrics Rouge L and Jacquard similarity surpass those of Grace, indicating reduced hallucination. Increasing the fraction of input tokens available during query reduces hallucination, with Jacquard similarity improving as the fraction increases. The authors investigate the unique opportunity to minimize hallucination by geometrically aligning the memory-computed readout vectors with right encodings. Observations from histograms of latent vector representations reveal that the Larimar decoder distorts the direction and magnitude of incoming readout vectors, making it challenging to connect the two vector types. However, when standard constraint generation is in effect, there is a clear alignment between Z-right and Z-readout vectors. Scaling up the length of Z-readout vectors by a fixed factor can minimize their distance to Z-right vectors, leading to hallucination-optimized generations. Table 1 summarizes the mean Rouge L scores for generated output with different scaling factors, with a maximum value of 0.72 achieved for a scaling factor of 4, significantly better than Grace. The benefits of scaling are also reflected in Jacquard scores. The alignment of Z-readout and Z-right vectors optimizes the geometric alignment between the two vectors and between the input and output vectors, which are not explicitly materialized and sit at the ends of the full Larimar model pipeline. The research on generation constraint scaling to mitigate hallucination focuses on optimizing vector distances and angles for enhanced performance. Figures 2 and 3 demonstrate the readout and generate pairs, highlighting the significance of geometric alignment. The Grace model, with its 1.5 billion parameters, requires 162.5 seconds to synthesize an entry, whereas Larimar, with 335 million and 810 million parameters in its encoder and decoder, respectively, takes 3.1 seconds on average. These complexities are crucial for understanding the efficiency and performance trade-offs in these models. The impact of scaling the generation constraint on mitigating hallucination in text synthesis models is explored. A table presents Rouge L scores for different scaling factors applied to readout vectors, revealing that as the scaling factor increases, the Rouge L score initially improves but eventually decreases beyond a certain threshold. This suggests an optimal scaling factor for achieving the best performance in terms of similarity to the input text. A visual representation of Jacquard similarity scores for various scaling factors is provided, comparing them to the ideal case in Larimar and the Grace model. The results indicate that while Larimar has smaller model sizes compared to Grace, it significantly outperforms Grace in terms of synthesis speed, demonstrating a trade-off between model size and computational efficiency. The importance of finding an optimal balance between model size, computational efficiency, and performance metrics such as Rouge L and Jacquard similarity scores is highlighted. This underscores the ongoing research efforts in optimizing text synthesis models to achieve high-quality outputs while minimizing computational resources. The paper explores the mitigation of hallucination in large language models through the use of generation constraint scaling. It highlights the Larimar encoder memory-decoder architecture, which allows for lightweight memory primitives to constrain generation in the decoder. This approach is shown to be more effective than training-based methods, such as Grace, in reducing hallucination. The authors present geometric alignment between input and output latent space representations, demonstrating the mean of vector distances and angles for different scaling factors. They emphasize that this technique can significantly improve the accuracy of generated text by aligning it with the input context. The paper also, a comparative analysis of wiki bio entries for Sir John Russell Reynolds, a British neurologist and physician, reveals significant discrepancies in accuracy among algorithms. The actual wiki bio entry provides a detailed account of Reynolds' life, education, and career, highlighting his birth in Romsey, Hampshire, and his gold medal achievements at University College, London. In contrast, the GPT-3 generated wiki bio entry incorrectly identifies Reynolds as an English lawyer, judge, and author, born in London, with a distinct educational and professional background. This entry details his education at Eton College and Trinity College, Cambridge, and his career as a lawyer, including his appointment as a judge of the Court of Common Pleas in 1867 and his knighthood in 1871. The Larimar-generated wiki bio entry also incorrectly identifies Reynolds as an English lawyer, judge, and author, combining elements from both the actual and GPT-3 generated entries. This entry presents a mixed account of his life, including his birth in London, education at Eton College and Trinity College, Cambridge, and his career as a lawyer. The Larimar with scaling factor s=4 generated wiki bio entry provides an even more inaccurate account, combining elements from the actual and GPT-3 generated entries. This entry incorrectly identifies Reynolds as an English lawyer, judge, and author, born in Romsey, Hampshire, with a father who was a professional in Parliament. In contrast, the Grace-generated wiki bio entry presents a more accurate account of Reynolds' life, correctly identifying him as a British neurologist and physician born in Romsey, Hampshire. This entry details his education at Repton, Romsey, and Trinity College, Cambridge, and his career as a physician, highlighting his graduation with an MB in 1851 and an MD in 1852, followed by his practice in Leeds. The entry also emphasizes his advocacy for women's and children's rights and his authorship on the law of copyright and the life of William Shakespeare.